In this demonstration, we will look at how using solid edge simulation can save you time and money during the design cycle of your products. You may have already seen the fundamental benefits that solid edge simulation provides, integrated virtual testing tools with the design engineer in mind. In this demonstration, we'll look at how the core capability extends into the areas of simulation, namely buckling. Here we have a large factory where we're adding a second floor walkway. It is important that the walkway be designed to safely support up to 60 people. With a display configuration, you can quickly get to the focused area of the walkway. First, let's get the frame columns added by turning on the solid we used to begin the design. Next, let's select the I-beam to be used for the new columns. Once selected, Solid Edge can quickly create the frames from a solid body, sketches, or a combination of both, as you see us do here. Now, the advantage of using the body is that if it changes, the frame automatically updates to that change. Now that the columns are in place, we're ready to create the first study, which will be a stress analysis. The first step is to define the geometry being used in the study. Next, let's quickly add a force that will represent 60 people that weigh an average of 165 pounds. You can access these tools from the ribbon bar at the top of the screen or from the tree, whichever is preferred. Notice that you can key in the preferred value of 10,000 pounds of force, and it will convert to your study's units, newtons in this case. Now, while applying the force, you have other options available, such as direction of force. Next, we're going to go ahead and get the columns constrained using fixed relationship on each of their bottom nodes. And then finally, let's go ahead and add a pin constraint to the back support from which the frame is bolted to the wall. Once the constraints are added, we're ready to mesh the framework. And one option is to show the mesh on close. So let's turn that option on. This gives us the opportunity to inspect it before solving the analysis. And here you can see the mesh looks great. So let's go ahead and solve this analysis. Solid simulation is powered by industry-proven Nastran and FEMAP technology. Looking at the results, you can see that the deformation is set to 10%, but you can set that to actual for a more realistic view. Let's also turn on the max marker to see where the greatest stress occurs. Notice that the max stress is 115, well below the yield stress of 262. In fact, it's a little over 2 times the yield stress and strong enough for our purpose in this design. So it's strong enough, yes? Well, for long, slender designs such as this, buckling is an important factor to consider, and Solid Edge is here to help with the ability to test that. Let's create a new buckling study to check this quickly. To save time, Solid Edge provides the options to copy any or all of the information from the first study to the new study, such as the applied load of 10,000 pounds of force and any of the constraints. From the simulation interface, you're able to work with several studies at one time, as well as monitor their status as it gives you live feedback. Once you've made some copies, you can also manually add other constraints. In this case, we'll go ahead and add those fixed relationships on the bottom as well. Now we're ready to create the mesh and get the results. Once in the results, you'll notice the eigenvalues are multipliers of the applied load at which the part or assembly becomes unstable. Generally, the lowest buckling value is where the failure will occur first. Study was set up using an option to give us 4 modes, as you can see here. In addition, there's an option to animate the results of the study, and in this example, multiplying the eigenvalue of 1.862 by the applied load of 10,000 force pounds, giving buckling value of 18,620. This shows it will fail before the yield stress of the previous study, so no, this isn't a strong enough design. Good thing we had Solid Edge to help us at this stage rather than a a costly or downstream mistake. Let's go ahead and improve the design. Now to do this, we simply change the size of the column that we used. By editing the frames, it's easy to select a different size. Once a larger column is used and applied, the study will show that it's now out of date. To update the study, let's quickly rerun the solve. By increasing the size of the I-beam, notice the new eigenvalue went from 1.862 to 5.560, or 55,600. These results give us confidence that the new framework will certainly withstand the original 10,000 pounds of force, as it is 5 times that value. Finally, all our analysis information can be documented by creating a report as you see here, either in HTML format or a Word document. In summary, Solid Edge Simulation provides design engineers accurate yet easy to use CAD integrated tools to ensure designs are fit for purpose, even in more advanced areas like buckling. Solid Edge, design better.